Hello, my AP students. Today we are going to get into what we like to call the bread and butter of physics. Now, the study that we are going to do today is of kinematics and of these equations that give you the power to predict the future. What do I mean by that? Well, let's take a step back and think about what we've been doing. We've been looking at motion a lot, and mechanics is the branch of physics that deals with the study of motion. And remember, we can split any kind of physics study into two really distinct parts: how something happens and why something happens. Kinematics does the how. How exactly do objects move? And while that might seem simple, like objects just move, mathematically we can really in-depthly express exactly how an object's going to move. Because we've studied 5 different characteristics that of objects' motion, really, that objects can have a displacement, and then over that motion of moving from one place to another, their speed can be constant or it can be changing. We can have it start at one speed and end at another speed. How long it takes to move that displacement depends on those speeds, and we can quantify that change in speed over time as acceleration. That is all of kinematics, and we're going to see how all 5 of those quantities relate back to each other. Dynamics, which is our next unit of study, is going to describe why do objects move and why does motion change. But we won't get ahead of ourselves yet. We're going to stick with kinematics. How can we describe how objects move? So kinematics, the basis of it is that with enough initial information, we can easily predict the motion of objects. If I tell you just a few key facts, like maybe about the initial speed and an acceleration, there's a lot of stuff we can figure out. So if we know how fast an object is going and its acceleration, we could figure out how long it takes to get to a certain speed. Yeah, we could do that. How about the distance it travels while getting there? Could we work back and figure that out? If I just know like the initial speed of a ball, and I know that sometime later it has a higher speed, has a higher final speed, and let's say I know like this distance, can I figure out what the acceleration must be from those values? And in fact, we can. We just need to use the correct kinematic equation. Our kinematic equation for constant acceleration, notice this is a key here, we see these 3 equations. And these equations are exactly what they look like. This equation will tell me what the final velocity is, what the velocity in the x direction is, given the initial, remember the 0 is not, so given the initial velocity in the x direction, and given the acceleration times the time. This equation will tell me what the exact position of an object is, given I know where it started, I know the initial velocity that it had, and I know the acceleration that the object had. This equation will give me the final velocity squared, and it's equal to the initial velocity squared plus 2a times x minus x naught. We often call this delta x, and I will abbreviate as such. I put them in this format because this is how they look on your AP Physics equation sheet, which we will probably see momentarily. So what am I supposed to do with those equations? Well, we are going to follow the RIPS method: read, identify, plug, and solve. And so a couple key pieces of information: assume initial position is 0 unless otherwise stated. So that'd be like this guy. We just are going to assume it starts at 0. And then whatever we calculate, if we just make this 0, will be the displacement. So that'll be an easy thing for us to do. Watch for the word rest or indications that something is not moving initially or finally. So initial or final, we can start at rest or we can come to rest, and that's an indication that either V initial or V final are going to be 0. And ask yourself, does the acceleration change in this problem? And if it does, then you have to be very careful to set up multiple parts. These are kinematic equations for constant acceleration. I cannot put in 2 different forms of acceleration into any one of these equations. Here, we notice, like, it's fine to have 2 different velocities. I can have an initial velocity and a final velocity. The same is not true for acceleration. Acceleration should be constant amongst all of these. All right, and so if we have multiple accelerations, we're going to have to split our work into multiple parts where we have acceleration remaining constant. And we'll see an example of this coming up. All right, so let's do an example of this. How far does a car travel? If it has an initial velocity of 4 meters per second, constant acceleration of 2 meters per second, and it travels for 30 seconds. So I have a couple key facts here, and I want to know something. I want to know, how far does a car travel? Well, one, what am I solving for? It's always a good first part of the problem. What am I looking for? I'm looking for displacement here. Well, what do I know? Identify my known variables. Well, I know that my initial velocity, v naught, is equal to 4. I know that my acceleration is a constant, 2 meters per second. 2. And I know that we do this for 30 seconds. And I want to find and identify a variable to solve for. That will always leave, so one, with any kinematic problem, there will always be 3 things that you know, and we see that here. And there will always be something that we are looking for. We're asked to find how far does it travel. Well, what does that leave out? What do I not know and not care about? My final velocity, v. So from my equations, I just didn't add those x's here. The x's are just kind of unnecessary. But you could put them there, whatever. But vx, like my final velocity, is what I really don't care for. I don't care to solve for this equation, so I'm going to need an equation that includes all 4 of these things and does not include my final velocity. So what equation of these does not include final velocity in it? I'm going to clear this, make it a little bit easier. This has final velocity in it. This has final velocity in it, but this equation has no Vx in it. It has Vx naught. We need to know the initial velocity, but we do not need to know the final velocity to use this equation. We can plug everything in here, and then we do know t, we do know a, we know t, we know v naught x, we know all of these things. We're going to assume that x naught is 0, and that's going to allow us to solve for what x is. And then we just plug in, and then we chug. So let's take another look at this. So what equation am I using? I'm going to use my second equation, x equals x naught plus vx naught t plus 1/2 axt squared. Plug in my known variables. So what's this look like? Again, I'm going to assume that we're starting at rest. We start at a speed of 4 meters per second. Our t is 30, 1/2 a, my acceleration is 4, 30 squared. And then that's all that there is to it. So once I plugged it in, now I just got to solve my equation, get my variables on one side, get my constants on the other, combine our like terms as we can. Here, I already got my variables all on the left, and then I just solve for what we got on the right. 4 times 30 is 120. 4 times 30 times 30 times 0.5 is 1800. And so my final answer comes out to be 1,920 meters. That is how far the car travels over this 30 seconds. Easy peasy. Let's try it one more time. Starting from a rest, an eagle flies a distance of 2 kilometers. So we learned 2 things from that statement there right there. Starting from rest, that's the easy thing to ignore, but that tells me my initial velocity is 0. An eagle flies a distance of 2 kilometers. I'm just going to express this as delta x equals 2 kilometers. And the bird's final velocity, v, is equal to 18. So I know initial velocity, final velocity, and displacement. I'm asked to find the average acceleration during this time. That means I want to solve for a. Then what is my odd man out? There's always 5 variables. There is always a displacement. There is always initial velocity, a final velocity, an acceleration, and a time. These will always be the 5 variables we're trying to figure out. We know displacement, we know initial velocity, we know final velocity. We are asked to solve for acceleration in this case. So that means time is my unknown variable. It's my unknown variable and the variable I need to exclude. Looking back at my equations, if I tried to use this equation right here, I would not know my acceleration and I would not know my time. An equation is impossible to solve for anything if we have 2 unknowns. We need to use an equation that does not have time in it. So there's only 1 unknown, and we can see the last equation fits the bill. And so, plugging in here, v squared equals v naught squared plus 2a delta x is just a rephrasing of this same equation. I didn't change much, nothing. I just didn't add the x's, and then I still called that naught, and then didn't add that x, and then x minus x naught, we just call that delta x. It's a lot easier to just say delta x. Plug in for our known variables. Well, we know our final velocity is 18. We square that. We know our initial velocity is 0. 2, a is what we are trying to solve for, and then delta x goes right there. Already, there's an issue though. This is kilometers. Everything else is measured in 18 meters per second. Our go-to should always be that both velocities are in meters per second, that our displacement is in meters, and our acceleration is meters per second squared, and our time is in seconds. If we do not include SI units and we try to mix these things around, you are going to get incorrect answers. So because everything else is SI, like we have a good time, or we don't have time included, we have our velocities both in meters per second. Displacement also needs to be in meters. So we can convert that real fast. How many kilometers are in a kilometer? 1,000. And so we went a distance of 2,000 meters. And now I'm trying to solve for my unknown. And we can go ahead and do some approximation. 18 squared here gives me 324 is equal to 2 times A times 2,000. Probably could have gone ahead and 324 equals 4,000 A. Divide both sides by 4,000. We got ourselves an answer. You can see we're going to have a small acceleration of 0.081 meters per second squared is our correct unit of acceleration. All right, so just from a few individual known variables, we can solve for our unknown. All right, let's try this one more. So here you can see that we have an acceleration of 1.2 meters per second squared, a final velocity of 15. We accelerate for a known time of 2.5, and we want to know what is his initial velocity, v naught. And what do we not know then? We do not know the displacement, and we don't care to. So notice my equation that I chose to use does not include displacement, but it gives me one unknown to solve for. Plugging in my values that I got above into the equation here, I just go through and solve, and we see that we have an initial velocity of 12 meters per second. And it's as easy as that. Kinematics is a lot of just identifying the correct variables, plugging it into the correct equation, and seeing what our answer comes out to be. So why don't we try a few on your own? So you guys can go ahead and pause this video and try out 2 of these problems. All right, your answers to these videos should come out to be 13.5 meters per second for the velocity of the boat, and then 33.3 meters for the displacement of the drag racer in the 3 seconds. All right, why don't we try another 2? Here's 2 more problems. See if you can get these ones and come out with the same answers that I do. All right, my answer for 3, we get negative 2.25 meters per second squared. Don't forget that negative there. Should come out to be negative. And then 4, we get after 5 seconds, the car's final velocity is 14, but after 10 seconds, the car's final position should be 146 meters away from where we initially started. Or not, 140 meters away from where we started, and then we include that 6 onto that calculation as our initial position. All right, and here's a much tougher problem. A Mars rover fell to Mars and used rockets at its base to land safely. The acceleration is 3.3 meters per second downwards. At 1,000 meters above the surface, the rockets begin to fire, giving the rover an upward acceleration of 4.0 meters per second squared. But we need to cancel these 2, that we have a downwards of 3.3, an upwards of 4, and so in our total acceleration upwards is 0.7 meters per second squared. The initial velocity of the rover was 38 meters per second downwards when it was 1,000 meters above the surface. What will its final velocity be upon landing? So this is just a kinematics problem. Now instead of forwards and backwards, we are doing up and down. Remember, in any physics problem, we can define what we want our coordinate system to be. And here we do have an upwards and a downwards. And I think I'm going to make my downwards my positive direction here, and my upwards my negative direction. And so why is that? Well, we could do it either way, but it's just important that I define it and I stick with it. So when I know my initial velocity is 38 meters per second downwards, I'm going to call that initial 38. My acceleration during this whole time is negative 0.7 because it's negative 0.7 upwards total, and upwards is my negative direction. What else do I know? I know the displacement, how far we are going to fall, is positive 1,000 meters because we're going to fall 1,000 meters downwards during this time. And what am I asked to find? I am asked to find the final velocity of this rover. And that final velocity is just then what I'm looking for. So with this information, we can put this together into a kinematic equation. We don't need time at all. And if we do this correctly, you should end up with an answer of 3.6 meters per second downwards is the final speed of the rover after it moves 1,000 meters. All right, another tricky problem. A car turns onto an entrance ramp to get onto a highway. The car begins at a speed of 1.5 meters per second and accelerates at a rate of 0.13 meters per second. The ramp is 100 meters long, and the car stops accelerating at the end. Then after merging onto the highway, it travels at a constant speed for 2 minutes at a constant speed. Remember what we said about changing acceleration. This is a two-part problem, meaning I literally need to examine these two parts separately. Because there's a part when we are accelerating, and then there's a part when we are moving at a constant speed. And we cannot look at those two things together. So, to answer the first part question, how far does the car travel after turning onto the ramp? Well, we know that the ramp is 100 meters long. And all I'm then trying to figure out is how far is the car going to travel in the 2 minutes it was going at a constant speed. Well, a really good thing to figure out would be, well, what is that constant speed it was traveling at? Because if it starts at 1.5, my initial velocity is 1.5, my acceleration is given as 0.13, and my displacement is given as 100, that's enough information to figure out my final velocity, right? The velocity it's going after it travels that 100 meters. It is enough information, and we end up with, I think, 5.3 meters per second there. Again, just using kinematics, we're going to use the third kinematic equation to figure that out. Now that I know what speed it's traveling at, I know it first goes 100 meters, and then it goes some delta x distance when I know that the Vx here was a constant 5.3, and I know that it was for a constant 120 seconds. Of course, 120 seconds, we can't use 2 minutes there. And then that's pretty easy to figure out what this delta x would be, what this displacement is. And then just working backwards that we don't even have to include the unconstant acceleration. Notice we actually still could use, during this time, this second kinematic equation, we could use x is equal to x naught plus v naught t plus 1/2 at squared. For this second part, we are starting at a position of 100. We have an initial velocity of 5.3. We are going to do this for 120 seconds. And our acceleration during the second part is 0. So we 100% can use this equation. We're actually just end up using the first part. Anyway, we come out with about 636, because then we add 100 to it. And we end up with a total displacement of 736. And again, looking at those two parts separately. We do the same thing for how long does it take the car to travel this distance. Well, we know how long this second part took. We know they traveled for 2 minutes for the second part. So the question really becomes is how long were we on the ramp for? And we can easily figure that out because we already knew this, our acceleration on the ramp. We know the initial velocity on the ramp. We even now know the final velocity is 5.7. We know the displacement of the ramp is 100. Do I have enough information to figure out how long we were on that ramp for? Absolutely. And we were on the ramp for about 30 seconds. All right, let me double check. 29 seconds is what we end up with, solving for this time there. And then so we spent 29 seconds on the ramp, and then we spent 2 minutes off the ramp at a constant speed. That's a total amount of time of 149 seconds altogether. All right, that was a changing acceleration problem. Let's see if you guys can do this one on your own. A missile is launched upwards from rest with an acceleration of 5 upwards and undergoes this acceleration of 20 seconds before the rocket gives out instantaneously. So not over time, it just was accelerating at 5 upwards, and then it immediately is now accelerating at 10 downwards, which is the acceleration due to gravity. How far upwards did the rocket travel? How long would it take the rocket to return through the ground? Again, 2 parts of motion. There's actually 3 distinct parts of motion here to separate things into. There is the rocket up. There is the other part when the rockets give out. So that's at this point right here. The rockets give out. And the thing is still moving upwards. So we have a no rocket up. And then there's a third part of motion when we just fall down. Fall down. And this makes sense too. So we are initially moving upwards, and we're at 20 seconds. We know that's how long this first part is. It lasts for 20 seconds. And then immediately the rockets just give out. So we're no longer accelerating upwards. Well, that doesn't mean you immediately start to fall. Like, it still is moving upwards. It's just now slowing down. It is going to take time to slow down, but still moving up in that process. So we can think of this first part as our speeding up, and then we are slowing down to 0, and then once we hit 0, we just fall down for however long that takes. So how far upward does this rocket travel? Well, we have two distinct parts of motion, right? So we know during this first part of motion, we could use, what equation makes most sense? We know our initial velocity is 0. We start at rest. We know that the acceleration is 5 up. And we know that the t is for 20 seconds, and I want to figure out how far upwards do I go. So I can use the second kinematic equation here. I end up just doing 1/2 a t squared, and that'll solve for my how far upwards I move. So that would be 20 squared times 5 times 0.5. We get 1,000. 1,000 meters is how far we move up in this first part. Mark that over here, 1,000 meters. Well, what about the second part? And again, think, why do I have to keep that separate? Acceleration is different. Now, in this case, I'm actually going to need to know what that final speed of the first part is as well, which I will figure out by doing v equals v naught plus a t. And I can figure this out. Because my initial velocity is 0, 20 times 5. That gives me a final velocity of my first part of 100 meters per second. And that's key to know that right here my velocity is 100 upwards, because then that final velocity of my first part becomes my initial velocity of this second part. So I'm just going to add that right there. That's 100. And then so now that I know this, I can figure what is, how far upwards does this whole thing, how far upwards do we go in this second time? So in my second case, my initial velocity, v naught, is 100. My acceleration is -10. I want to know what my displacement is, and I know that my final velocity in this case is 0, because we are going to come to rest at this point. So now with that information, can I find displacement? I absolutely can. And then I come together to find that we move another 500 upwards. So we moved 1,000 meters with the rocket, 500 meters without the rocket, and then that's a total of how far upwards do we go? 1,500 total. Now we also want to do a similar thing when solving for time, and that's what I'm doing in my second part. And you can kind of see now that I have this divided, how would I do this? Well, there's a time for a first one. We have to get the time with the rocket, the time without the rocket, so slow down but still moving up, and then we can solve for that one. And then our time that it takes to fall the 1,500 meters downwards, and then you just put all 3 of those times together. All right, so with the changing acceleration, the main key takeaway here is it's important to analyze each part of motion separately, or else it's easy to get confused. Make sure we're labeling things clearly, and a drawing is always helpful.